G'day, this is Chris, the Guitar Amp Tech from Sydney, Australia. My original thoughts were I wasn't going to videotape this repair of a Princeton Reverb reissue. But then I thought, it raises some interesting issues, some interesting questions. Whether you are a tech or whether you are a owner of an amp, I guess we have to look at some of these issues. So it's a question of balance. How much do you spend on an amp to repair it? I mean, there's obviously the fault at hand, which you'll see shortly in this, which has to be repaired. But then some amps, the manufacturer has to make decisions about where they're going to place it in the market, and they make decisions to reduce the quality on some items to keep the cost low. We hate low-cost items until we're paying for the amplifier, till we're buying the amplifier. Then we want a low-cost, great-sounding amp like this. But Fender had to make pricing decisions. Do I now repair all of the potential problems and bill the client, or do I just repair the fault at hand? That's something we're going to look at now. So go get yourselves caffeinated, come back, and let's have a closer look. All right, here we are inside the chassis, and looking around we can see that has had a major burnout, and that, I'm pretty sure, is the dropping resistor from our reservoir cap. Where are we? Here's our reservoir cap. Yeah, it's the first capacitor there is C28. Then we have R58, that one there. Ironically, there is a fuse in series with it, a 7 amp fuse, which I think is this, yeah, it's that one there. So it's a little solid state fuse that's in line with that resistor. So in this case, we're glad that that resistor burned up to save the fuse. Yeah, crazy, what do you say? So why would that resistor there have blown? We've seen a lot of current draw. Did it come through this side of it, or did it come through that side of it? This side of it's going to go to the B+. This side of it is going to go to the screen. So almost definitely I'd be thinking a tube, one of our power tubes, has failed. Either this one or this one. So I'm going to check those. So what are we going to do now? So I spoke to the customer. I said the easy thing, or the cheapest thing, is just to replace this. Probably need to replace the pair of 6v6s, and it'll be up and running. Now, I did test all of these capacitors. There's 4 here, 3 there and 1 out of sight that way. Sorry about the cut finger. And I've measured them all. They're okay for capacitance, but all of them are either right at the limit of ESR or over the limit. As I explained to the owner, it's a sign that we're getting to end of life. So this amp was made in 2019, what's that, it's 25 now, 6 years ago. I've seen these things failing as young as 3 years old. The fact that we got 6 years out of them is not too bad. I spoke to the owner with a couple of different levels of what we can do, and get the feeling that the owner would like to upgrade the speaker in this, which I fully endorse. So we're going to make some more cost-based decisions on this repair. We have to do that. These things I strongly recommended that we do, and he agreed to that. So we'll replace these 4 IC branded caps. A couple of other would it be nice things to do. So we've got here 2, 1, 2. These are our screen grids. These can also fail, and when they fail fairly dramatically. And because, once again, like this, it has been soldered hard onto the circuit board, it can damage the circuit board, and I've seen amps with a hole burned right through the PCB. We decided to go for the lower cost option, which is just to replace both of these with longer legs so I can elevate them off the PCB. And this I'm happy to do at no cost. And that's going to be 70% more secure than leaving them where they are. 100% more secure, obviously, put them on the sockets, but let's save our money and put it towards a speaker. I'm not too keen on these ground connections where they're just screwed into the chassis with sheet metal screw, I think. Yes, it's sheet metal screw. So that's going to come out. I'm going to replace that with a nut and bolt. Another thing which we've seen burn up a few times are these two 100 ohm hum balance resistors or heater balance resistors. I'm going to take those out because I've got to lift the PCB to do this anyway. I'm going to take those out and put them on the directly onto the heater wires to ground. Another thing you see with Princeton's is this one goes to the B+, that's the highest voltage. Next step down goes to the screen. Next step down, what? Next step down's unused. Why is that? Then it goes down another step to go to Y, which is what our power supply is for our phase inverter. So what I'm going to have a look at is just relocating our phase inverter from that position to this unused node there. The increased plate voltage will give us a little bit more dynamic range and hopefully a bit more clean headroom. Okay, PCB is going to have to come out. So these sockets here are going to get unplugged. My aim is to flip the board up this way. To do that, I'll have to remove that earth cable. I'll also just remove the bias pot. I'll cut all of these, give us a bit of length in that. And we'll see if I can avoid removing these spade connectors, I will. But we'll see how we go. Let's have a look at what I've been up to. So the goal has been making the amp more reliable, avoiding damage to the PCB when a component failure occurs. Could I have taken things further? Yes, I could have, but I'll show you what I've done, and for cost reasons that I've made certain compromises. So you can see here, two resistors have been removed. These are the hum balance resistors, the heater balance resistors. I've moved them from there on the PCB because I've seen these burn up a few times, and I've relocated them to come off the 6.3 that feeds the indicator lamp. And I'm using higher wattage, not that they're really drawing much current. That's bolted to that transformer leg and bolted to the chassis there. The mains ground, which was held on by a sheet metal screw, I don't know if you can see it there, but that is now a nut and bolt with a nylock lock nut on there holding it to the chassis. I just feel more comfortable about that never coming loose. The dropping resistor for that node resistor that had burned is now gone. There's still a little bit of a scorch mark on the PCB, which you can't see, it's hidden under there. But I've looked through that scorch doesn't go through the PCB. And I've now got a higher wattage resistor elevated off the PCB, which is that there. The next dropping resistor also elevated off the PCB and mounted there. The screen grid resistors, so high wattage resistor elevated off the PCB. I'm quite happy with that. So you can see I've upgraded the capacitors, all of the leaking IC caps have been removed. So I've put in a larger 40 microfarad for the first reservoir cap. As the name implies, it's going to be the reservoir of energy when there is a sudden demand by the amp. So I'm happy to put that at 40 microfarad. It's well within the first filter limitation of a GZ34, which I think from memory is 60 microfarad. This is still 40. Offers a way better reserve of energy than the 20 microfarad originally. and it won't make the amp stiff. The screen grid, I also like that to be a little bit more solid, so I've gone from 20 to 30 there. And the other two main filter caps I've left as 20 as per original, because that's where, you know, it can stiffen up if that's too big a value. You'll notice that the capacitors have the writing of the values facing upwards for the next tech to be able to go, oh, I see what he's done here. Now R17 here is the plate resistor for the phase inverter, and it goes to, this is the next dropping resistor. Let's have a look at the schematic. There's our B plus with that first dropping resistor. Then we have our screen grid resistor with our next dropping resistor. Then we have an unused node on R57. So, and then the Y, point indicated Y, which will go to the phase inverter, I have now relocated it from that side of R57 to the other side of R57. And you can see that link there. I intentionally did it on the top side of the PCB rather than underneath. To do it underneath would require cutting the track that is between there and there. But even more importantly, I want future tech to be able to see what I've done here and hopefully understand why I've done it. Just in case the owner at any stage changes his mind and goes, you know what, no, I think I like it, preferred it the way it was before. So it is now visible, and I intentionally lifted this leg out, but I haven't cut it off, so future tech can just remove my little jumper lead, can now put R17 back through the hole, solder back on where it was onto the pad before, and the amp back to original. So pretty easy to reverse, pretty easy to spot the way I've done it. What I've also done is I've added a grid stopper to the phase inverter as well, and that is under there. What do I put in there? Okay, yeah, I usually put in something like 330 or 470, so in this case I put in a 470k resistor as a grid stopper, because stock, it doesn't have a grid stopper, and I've done it for two reasons. One, the usual reason for putting in a grid stopper in terms of oscillation, but I've also put it in there to reduce the chance of the phase inverter being hit too hard and giving us distortion. I'm going to show you how I bias an amp. Now I've got to say, the old Fender amps, the estimate of this bias voltage was always remarkably, spookily accurate. But let's just check to see how accurate this is. It's saying minus 40 volts is where to do it. The reason I don't like setting it by voltage is because each one of these valves are different. And if we put in a different set of valves, it may be 38, it might be 42. I don't believe it's going to be minus 40. I hope I'm proven wrong and it is minus 40, but we're going to do it the way I do it. I don't even do it by current. I use current as a, plate current, as a double check. But the way I set the bias is specific to each tube. Each tube, I know exactly how it's going to operate. And I do that by injecting a sine wave into it. I will set the bias control to maximum cold, and then hopefully we'll see the crossover distortion on the oscilloscope. And then I start increasing that bias voltage, reducing the negative, and making the tubes hotter and hotter and hotter until we see that crossover distortion disappear. Then I will check to see where it fits in on the current. Are we in a safe current range? And then we will just, out of interest, see how close it was to Fender's estimate of minus 40 volts. All right, first thing we're going to do is power it up on the current limiter and make sure I haven't made any boo-boos. You can watch the current limiter there. That looks good. Let the tubes warm up, make sure there's no shorts happening anywhere. Glowing a bit brighter now as the power tubes begin to conduct. Okay, don't think there's anything problematic there. Let's put it on full current mode now. That current is reading at very low current draw. Looks good. Plate 470. Screen 455. Minus 40 on the control grid, which is exactly where that schematic is saying it should be. But what we're going to do now is I'm going to start winding this bias pot. I want to go to the most negative number I can. And that's it, just there. I want you to just watch that screen as I start to increase the sine wave that's going into channel 1, or input 1 I should say, not channel 1, it's a single channel amp. And let's just watch to see, let's get rid of that yellow trace. There we go. You should see a pretty ugly signal here. Okay, you can see that vibrating away. I've got the intensity up on 6. Let's get rid of that. That's solidified it a lot. Pretty ugly looking sine wave there. Now what I'd like you to do is just watch that display as I start to increase the volume of the sine wave. And you'll see here we've got a pretty good match between our tubes, but running way below spec. So I'm now increasing the volume. Signal looks pretty good, but I reckon, and there we go. You can see the crossover distortion here, where it crosses over the 0 point. And let's just keep increasing it till we get. Now I expect this is going to be a bit of asymmetric clipping here, which is another characteristic of a cathodione phase inverter. Alright, so now what I'm going to do is just slowly start increasing the bias voltage, and we should see both the gain of the sine waves increasing and a reduction in the crossover distortion. I don't know about you, but I can't see any crossover distortion at that point. Now I'm going to turn the volume knob. What volume are we on? We're on about just under 5. And I reckon that's pretty much, yeah, there we go. We can see asymmetric because it's clipping more on the top and the bottom still nicely rounded. So let's turn that volume right off. And let's check to see what our bias currents are. 20 and 21. We can see the tubes are very well matched. These are JJs. And now let's just do a little bit of arithmetic. We'll go on this one because it's slightly higher. Let's go 0.022 amps times 450 volts equals 9.9. That's high. Divide that by 14 watts per 6v6. and that's 70%, 70.71%. See, our sine wave tells us spot on. Our current, I would like to see a Princeton somewhere between 50 and 65. So I'm going to ramp this up again. And I'm just going to see if I can cool it down just a whisker without introducing any more crossover distortion. I think I can just see a little bit of a crossover notch there, very faint. Let's just double check our currents now. 17 and 19, let's go on this one again. 0.019 times 457. 8.68, divide that by 14. I think this is going to be the money one. 62%. I'm very happy with that. Crossover distortion is all but gone. But because I'm a pain in the ass, I'm going to just notch that up just a little bit. Okay. Check my notching. There we go. That's pretty much perfect, actually. I'm going to call that maximum volume, and that's, you can't see my other meter, but it's 12.1 volts AC RMS. 12.1 squared divided by 8 ohms. 18.3 watts RMS. That's pretty damn good. I think this amp's rated at 15. So I would say we've got that exactly on the money now. So 22 milliamps. Let's just double check. 0.022 by 455 equals 10. Divide that by 14. 71.5. All right, I'm going to stay with that. A little bit hotter than you'd normally go on a Princeton. I'd normally go 65 as at the hot end, but that's what these tubes want. And that's why it's important to measure it on the oscilloscope to watch that crossover distortion, double check it against the current to make sure we're not exceeding anything. And now let's measure that voltage and see what the voltage is. And see how close it was. What was it, 40 volts, was it? 40 volts. Let's see how close we are to Fender's spec. God love you, Fender. One says a slight difference in the draw of the current. Why? Could be the tubes. We can see there's a small difference in the tubes. Also, these 220k resistors, if they're not identical, that's going to slightly change it. Our screen resistors are going to slightly change it. That is well and truly within spec. Once again, Fender, extremely close, but I'm now more confident that we've done it this way. So we are going to call the bias exactly right. All right, let's give it a listen to see if we can hear any weirdo sounds. Sounds bloody awesome. Awesome. Let's put it back together. All right, now we're going to do a sound comparison between the original Fender speaker that's in here, and in here I've got a Weber DT10P, which is what I put in my Vox AC10, which I like a lot. So we'll do a comparison and just be able to advise the customer, look, it's a worthy expense to go to, or the difference just isn't that great. So we'll see. A little bit of tape here, so on each one, so I can put the mic in the same place, same settings on the recorder and everything like that. So I like to have the mic facing halfway between the edge of the cone and the center of the cone. What have I got? I've got treble on 8, volume, let's put the volume on 4. And this would have been breaking up before, but we've got a little bit more clean headroom now because of the change I made to the phase inverter. Bass is on, let's put it on 5. Reverb off because I've got no tank hooked up. Intensity off. Okay. Bit of buzz, single coils, what do you do? The only way you're going to get that sound is to put up with the buzz. Okay, I'm very interested to hear this. Now the Weber's a brand new speaker, it's never been run in, so it'll get better with time, but let's see what it sounds like straight off the bat. Definitely much bigger bottom end than on the Fender, which is a good or a bad thing depending on how you feel about bottom end. Let's just try something a little bit cleaner. Let's bring this volume down to 3.5. So this time we'll try the Weber first. Okay, let's try the Fender. Middle position. Very, very interesting. I don't know if you can hear it through all of the treatments that it goes through to get to your ears. But here, yeah, vastly different. This has got way more, I don't want to call it boxy mids, but I'm going to call it boxy mids. That's way more of a pleasing sound. This is definitely not a bad sound. That is a great sound, and I know it's going to get greater as that speaker runs in. So that's what I'll tell the owner, and depending on whether he wants to pay the extra expense from having a perfectly adequate speaker to a much better speaker. And as I said to him, when you get a better speaker, always put your original speaker in a safe place, and when you eventually come to sell that amp, you're going to take that good speaker out, put the original speaker back in, and that speaker will then go into your next amplifier. Like the first Weber speaker I bought off Ted Weber directly when he was still with us was, had a different name back then, C something or other. I think basically that same speaker is called a Blue Dog today. It's now doing service in its fourth amp, my Marshall 18-watt hand-wired one. It's been through a PV Classic 30. It's been through, it's a 12-inch by the way. An AC10, AC15. So great speaker.